Why, with powerful cranes, computer modeling, and advanced materials at our disposal, do we spend years doing what the ancients built in a matter of weeks? The Roman Empire covered the world map with a network of roads, bridges, and fortresses at a speed that seems physically impossible for people armed only with pickaxes and shovels. Modern engineers often attribute this to slave labor, but the truth lies in a completely different level of process organization. The Romans did not just build, they turned war into construction, and construction into a perfectly tuned conveyor belt that worked without a hitch. Their secret lay not in muscle power, but in a system that transformed the chaos of the wild into an orderly civilization with frightening efficiency. Watch the video to the end, and you will learn how Roman legionnaires used a unique engineering algorithm that allowed them to build impregnable fortresses on enemy territory in just a few hours before sunset. What if I told you that everything you believed about Roman soldiers is not true? We are used to seeing legionnaires exclusively as warriors clad in armor and clutching gladiuses, ready to battle barbarians. However, the reality is that for most of their service, these men did not wield swords, but axes, saws, or baskets for earth. The Roman legion was not just a military unit, but a mobile construction corporation with incredibly highly skilled employees. Each recruit underwent a rigorous selection process where not only his physical strength was assessed, but also his ability to learn crafts. Instead of grueling fencing training, soldiers spent hours learning to dig trenches, fell trees, and cut stone under the strict supervision of engineers. Each legionnaire carried an impressive set of tools that weighed more than his weapons and armor combined. This set included a pickaxe, a shovel, a measuring chain, stakes for a palisade, and a basket for carrying soil. This allowed the command to turn a combat unit into thousands of skilled laborers at any moment. No modern army has such a high percentage of versatile specialists ready to instantly swap their rifles for trowels. The uniqueness of the system lay in the total specialization within each small unit, called a contubernium. In this group of 8 people, each knew their construction role by heart. One was responsible for felling trees, another for trimming them, a third for digging, and a fourth for preparing food for the workers. This eliminated downtime and unnecessary discussions that so often slow down modern projects. The commander did not need to explain the task. It was enough for him to indicate the place and time of completion of the work. The officers of the engineering corps, or camp prefects, were true architects with the authority of generals. They did not sit in offices but were directly on site, controlling each stage with mathematical precision. They had no room for error, as a poorly constructed bridge or wall could cost the lives of an entire legion. Their drawings were not on paper, but in their heads and on wax tablets. Yet the precision of their execution is still impressive today. This rigid hierarchy of responsibility created a structure where negligence was simply impossible. The Romans' tools, primitive at first glance, were the height of ergonomics and functionality for their time. The famous delabra, a combination of an axe and a pickaxe, became a symbol of Roman engineering expansion. It could be used to chop down the roots of centuries-old trees, loosen stony soil, and even break through the adobe walls of enemy fortifications. The iron for these tools underwent special hardening so that it would not dull when striking hard rock. Standardization of equipment made it easy to replace broken handles and blades right in the field. The speed of work was also ensured by the absence of the need to coordinate projects with numerous authorities and landowners. The Romans came to a new territory, declared it the property of Rome, and began to change the landscape at their discretion. Mountains were torn down, forests were cut down, and swamps were drained without environmental assessments or public hearings. This ruthless determination allowed them to build straight roads where others would have spent years winding around. Engineering dominated the natural terrain, subjugating it to the needs of the empire. An important factor was the motivation of the soldiers themselves, who were building not for an abstract customer, but for their own safety. The legionnaire understood perfectly well that whether he would wake up tomorrow morning depended on the height of the rampart and the depth of the moat. This personal interest in the quality of the work created a level of quality control that was unattainable for hired workers. no one cut corners when their own lives and the lives of their comrades were at stake. Collective responsibility bound the bricks and logs more firmly than any modern cement. In addition, the Legion was a completely autonomous organism that produced all the necessary materials on its own. The field workshops employed blacksmiths, carpenters, tanners, and masons of the highest caliber. They did not have to wait for supplies of nails or staples from the metropolis. They forged them on the spot from captured or mined metal. Brick factories sprang up in the middle of nowhere in just a couple of days, supplying the construction site with ceramics. Such a closed economy made it possible to carry out construction anywhere in the known world. The organization of labor resembled a giant anthill, where every movement had a meaning and a purpose. Thousands of people moved around the construction site without interfering with each other, thanks to well-established routes and schedules. Trumpet signals announced changes in work stages, meal breaks, and guard changes. This rhythm, set by the sounds of the horn, put people into a state of flow, where fatigue faded into the background. Discipline turned hard physical labor into a ritual of service to Rome. It was this approach, where each soldier was both an engineer and a worker, that allowed Rome to build infrastructure at an alarming rate. They did not wait for contractors. They themselves were the best contractors in human history. The Legion came to the desert and left behind cities, roads, and aqueducts. I wonder how this topic is perceived in different parts of the world, and whether you agree that the versatility of a soldier was more important than his combat skills. I would be very interested to hear your point of view. Please write about it in the comments. Are you ready to learn the truth about how the Romans invented modular construction thousands of years before us? The secret to the incredible speed of Roman construction lay in the total, uncompromising standardization of all elements. The Romans were the first to understand that uniqueness is the enemy of speed, and uniformity is the key to efficiency and quick repairs. They developed a system of weights and measures that worked from foggy Britain to the hot sands of Syria. A brick made in Gaul was a perfect fit for a wall built in North Africa. A military camp, or Castrum, was always built according to the same approved plan, regardless of the terrain. A legionnaire transferred from one end of the empire to the other could find the warehouse, hospital, or commander's tent in the new camp with his eyes closed. The main streets always intersected at right angles, forming a perfect cross in the center of the settlement. The width of the streets, the distance between the tents, and the depth of the moats were specified in the statutes with centimeter precision. This eliminated the need to redesign the settlement each time, saving precious time. Wooden structures for bridges and fortress walls were prepared in advance according to uniform templates. Logs were cut to a specific size, and grooves and spikes were carved so that they would fit together without additional adjustment. It resembled a giant construction set, the parts of which could be assembled in any sequence. If a beam broke or rotted, it was replaced with an identical one taken from the warehouse. There were no individual measurements or on-site adjustments, only the assembly of ready-made elements. The dimensions of stone blocks for the construction of aqueducts and public buildings were also subject to strict standards. Quarries produced blocks of specific sizes, which simplified transportation and laying. Lifting mechanisms and cranes were designed specifically for these weights, which prevented overloads and accidents. An architect could calculate the amount of stone needed while sitting in Rome and be sure that his order would be understood in the provinces. This standardization allowed for incredibly accurate logistics planning. Even roof tiles had a standard shape and size, approved by state standards. Many bricks and tiles were stamped with the mark of the manufacturing legion, which was a sign of quality and responsibility. This made it possible to quickly cover huge areas of barracks and warehouses without wasting time selecting materials. Factories worked around the clock, stamping out thousands of identical products. The standard shape of the tiles also ensured perfect water drainage and protection against leaks. The width of Roman roads was strictly regulated by the law of the 12 tables and averaged about 4 to 6 meters. This allowed 2 carts or troops to pass each other without congestion or collisions. The depth of the roadbed and the composition of the layers were also standardized to ensure durability. The track gauge of the carts was standardized so that the wheels would fit into the ruts already worn into the stones. All transport traffic in the empire moved according to uniform rules and dimensions. Standardization even extended to such details as lead pipes for water supply, which were produced in specific diameters. This allowed engineers to accurately calculate the water pressure and throughput capacity of the system. Connecting elements and taps were compatible with pipes in any city of the empire. Repairing the water supply system did not require the manufacture of unique parts. It was enough to take a spare part from the warehouse. This made the urban infrastructure reliable and repairable. Thanks to this system, the Romans were able to involve the local population, who were not highly skilled, in construction. All they had to do was give them a template or measuring stick and show them a simple operation. Under the guidance of Roman engineers, the barbarians became part of a great construction machine. Complex architectural tasks were broken down into simple, repetitive actions. Standards replaced craftsmanship, allowing high quality to be achieved by mass forces. This approach eliminated creative struggles and disputes on the construction site, speeding up the decision-making process. If there is a standard, follow it. If there is no standard, use the closest suitable analog. Innovations were implemented centrally. If a new type of joint was invented in Rome, instructions were sent to all legions. The system was updated as a whole, like software on modern computers. Design errors were identified and corrected systematically, not locally. Thus, the Roman Empire was the first state to introduce the principles of industrial production into construction. They conquered time and space not with magic, but with order and unification. Each building was a brick in the huge edifice of Roman civilization. Do you think such strict standardization kills architectural beauty, or is order itself beautiful? Want to know a secret that will change your perception of concrete? What we now call concrete was invented and perfected by the Romans more than 2,000 years ago under the name opus cementitium. This material was a real revolution, allowing them to abandon the simple piling of stones and begin to cast buildings of any shape. But the most surprising thing was not the fact that mortar was used, but its unique chemical composition, the secret of which we have only recently unraveled. Unlike modern concrete, Roman concrete did not weaken over time, but only became stronger as it reacted with the environment. The key ingredient in this miracle material was volcanic ash extracted near the city of Pozzuoli. This ash, called pozzolan, contained special minerals that, when mixed with lime, triggered a complex chemical reaction. Unlike modern mixtures, Roman concrete did not simply dry out, it crystallized, forming strong bonds at the molecular level. The mixture was so dense and waterproof that it could be used to build ports directly in seawater. Salt water did not destroy it, but rather strengthened it, making the structure eternal. The process of making concrete was hard physical labor that required careful adherence to proportions. Workers manually mixed lime, pozzolan, water, and filler made of small stones or broken bricks. The mixture had to be thick enough not to spread, but plastic enough to fill all the voids. The quality of the mixture was controlled by experienced craftsmen who determined the readiness of the solution by eye. The fate of the future arches of the Colosseum and the dome of the Pantheon depended on this. The formwork for pouring concrete was made of wood and was a true work of carpentry art. It had to withstand the enormous pressure of the liquid mass without deforming or leaking mortar. The inner surface of the boards was carefully treated to ensure that the walls were smooth and even. The complex curved shapes of the arches and domes required precise calculations and skill in creating the forms. After the concrete had set, the formwork was removed, revealing a monolithic structure with no joints. The Romans often used concrete as the core of a wall, facing it with brick or expensive stone on the outside. This saved valuable materials while maintaining load-bearing capacity and a monumental appearance. From the outside, the building looked like a marble palace, but its skeleton was cast from rough but incredibly durable concrete. This technology accelerated construction many times over, as it did not require a perfect fit of the internal stones. The wall grew layer by layer, turning into a single monolith. The use of opus cementitium allowed the Romans to span huge spaces without using columns. The dome of the Pantheon remains the largest unreinforced concrete dome in the world. Engineers lightened the structure by adding lightweight pumice to the upper layers instead of heavy rubble. It was an ingenious engineering solution based on a deep understanding of the properties of materials. They manipulated the density of concrete as easily as we change settings in a program. Special wooden tampers with metal tips were used to compact the mixture in the formwork. Workers spent hours beating the wet concrete, driving out air bubbles and achieving maximum density. This monotonous work was critical to the durability of the structure. The slightest void could cause a crack in 100 years, and the Romans built for millennia. Each blow of the rammer was a contribution to the eternity of the empire. Concrete allowed for fast and cheap construction, using local materials and unskilled labor for mixing. There was no need to transport huge blocks of granite from Egypt. It was enough to find limestone and volcanic ash. This democratized construction, allowing baths, theaters, and aqueducts to be built even in remote provinces. The Roman way of life spread along with the technology of liquid stone. Surprisingly, after the fall of the Roman Empire, the recipe for this unique concrete was lost for many centuries. Medieval builders returned to stone and mortar, forgetting about the possibilities of monolithic casting. Only in our time have scientists been able to completely restore the composition and understand why Roman breakwaters have stood for thousands of years, while modern ones collapse in half a century. It turns out that ancient technologies sometimes surpass modern achievements in chemistry. This material became the physical embodiment of the Roman spirit, durable, reliable, adaptable to conditions, and created for eternity. If you enjoyed learning about the secrets of ancient technologies, be sure to like this video. And don't forget to subscribe to the channel so you don't miss any new videos. Guess how long it took to build this? The Roman road network is not just a network of paths for carts. It is a complex engineering structure that surpasses the Great Wall of China in scale. The total length of Roman roads was hundreds of thousands of kilometers, encircling the Mediterranean with a dense ring. These roads were not built for merchants, but for the army, so that the legions could march at maximum speed in any weather. The arrow-straight highways ignored the terrain, cutting through hills and straddling gorges. Road construction began with surveyors using special tools such as a gromma to lay out perfectly straight lines. They mapped out the route, trying to avoid sharp turns that would slow down the movement of the formation. Then the legionnaires dug a wide trench, reaching solid mainland soil. This was the base, the foundation on which the entire structure would rest. No dirt or soft soil was to remain under the roadbed. A Roman road consisted of 4 main layers, each of which served a specific purpose. The first layer, the statumen, consisted of large stones laid by hand at the bottom of the trench. It served as a foundation and provided drainage, preventing water from accumulating under the pavement. The stones were tightly fitted together to create a rigid base. This ensured that the road would not sink even under the weight of heavy siege engines. The second layer, the rudus, was a mixture of crushed stone, broken brick, and lime, which was carefully compacted. This layer acted as a shock absorber, distributing the load from wheels and feet across the entire base area. It was flexible enough to withstand vibrations, but firm enough not to deform. This layer could be up to half a meter thick, providing incredible strength. It was a concrete cushion hidden beneath the surface. The third layer, the nucleus, consisted of fine gravel and sand, also bound with cement mortar. It leveled the surface and served as a base for the final coating. This layer was carefully profiled to create the convex shape of the road. The center of the road was always higher than the edges, so that rainwater would instantly drain into drainage ditches. Roman roads always remained dry and clean, even during the heaviest downpours. The top layer, the summum dorsum, was laid with large flat slabs of basalt or other hard stone. The slabs were fitted together with such precision that it was impossible to insert a knife blade between them. The surface was smooth for wheels but rough enough to prevent horses' hooves and soldiers' caligae from slipping. It was a permanent covering that had been polished for centuries but had not deteriorated. Deep drainage ditches were dug along the roads to drain water. The Romans understood that the main enemy of the road was not the load, but water, which erodes the foundation and destroys the surface when it freezes. The drainage system worked flawlessly, keeping the roads in perfect condition for centuries. These ditches were often reinforced with stone or wattle to prevent the soil from crumbling. Every 1,000 steps, a milestone was placed on the side of the road, a massive pillar with information about the distance to the nearest city and the name of the emperor who built the road. This was the world's first road navigation system, allowing travelers to accurately calculate their travel time. Travelers always knew where they were and how far they had to go. The roads were also equipped with post stations where couriers could change horses. Thanks to this multi-layered pie, Roman roads withstood enormous loads without repair for centuries. Many modern highways in Europe are laid directly on top of ancient Roman roads, still using their foundations. This shows that the engineers of the past built in a margin of safety that is excessive even for modern technology. They did not build for a season, but for eternity. The speed of travel on such roads was phenomenal for the ancient world. Legions could cover up to 30-40 kilometers a day in full armor, moving their forces faster than the enemy could learn of their approach. Roads were a weapon that allowed Rome to control vast territories with minimal forces. In the next chapter, you will learn how the Romans solved the problem of supplying these gigantic construction projects with food and materials. Any construction project, even the most ingenious, is doomed to failure without a clear system for supplying resources. The Romans were masters of logistics, turning the delivery of goods into an exact science. In order for the legion to build, it needed to eat, drink, and receive materials on an industrial scale. Huge caravans of carts drawn by oxen and mules followed the army, carrying grain, tools, and metal. Quartermasters calculated the army's needs with an accuracy of a handful of grain per person. Particular attention was paid to water transport, as it was the cheapest and fastest way to deliver heavy cargo. The Romans used rivers and seas as their main transport arteries, bringing stone and timber as close as possible to the construction site. Special flat-bottomed barges could enter shallow waters, delivering cargo directly to the construction site. Port infrastructure with cranes and warehouses was built in parallel with the main facilities. The river became a conveyor belt feeding the construction site. Food supplies were organized through a network of warehouses and granaries located along strategic roads. The local population was taxed in kind, supplying grain, meat, and wine for the army's needs. This allowed the legions to focus on their work without wasting time searching for food. Field kitchens operated around the clock, providing soldiers with high-calorie food for hard labor. A well-fed soldier built faster and better. Building materials were procured with a view to minimizing transportation costs. Roman geologists and explorers surveyed the area in advance for quarries, clay, and forests. The legions tried to use what was available locally, adapting their projects to local materials. If there was a forest nearby, they built with wood. If there was stone, they opened a quarry. Flexibility in the choice of resources was the key to speed. The forest was cut down and processed by special teams that went ahead of the construction columns. The wood was dried quickly or used raw if the structure allowed for shrinkage. For critical components, seasoned oak was brought in from distant provinces. The organization of logging resembled an industrial enterprise with division of labor and production control. Wood chips and scraps were used as fuel for kitchens and kilns. Stone extraction was mechanized as much as possible in ancient times. Wedges, winches, and block systems were used to move huge boulders. Stone cutters rough-cut the blocks right in the quarry so as not to carry extra weight. Each block was marked so that the masons on the wall knew where to place it. It was a just-in-time system powered by muscle power. Metal for nails, staples, and tools was transported in ingots and reforged in field forges. Legion blacksmiths could repair any tool or make a new one in a matter of minutes. Scrap and broken parts were not thrown away, but sent for remelting. Waste-free production was the norm in Roman camps. Iron was valued as highly as gold and was accounted for in strict reports. Organizing the water supply at the construction site was a critical task. Without water, it was impossible to mix mortar and provide drinking water for thousands of people and animals. The first thing to do in a new location was to find sources and lay temporary pipes or channels. Water carriers constantly shuttled between the river and the construction site. Dehydration could stop construction faster than a barbarian raid. This gigantic flow of resources was managed by the legion's headquarters using a complex bureaucratic system. Scribes kept track of every sack of grain and every beam, preventing theft and shortages. Report cards circulated between units, creating an information network. The Romans conquered chaos with numbers and lists. This invisible but colossal work behind the scenes ensured the phenomenal pace of construction. A legionnaire on the wall could lay bricks without thinking about where they came from or whether he would have dinner. The supply machine worked smoothly, grinding the empire's resources into monumental grandeur. What I am about to show you is banned in 12 countries as an example of a risky engineering solution, but for the Romans it was the norm. Bridge construction was the pinnacle of Roman engineering, a demonstration of complete superiority over the forces of nature. Julius Caesar built a bridge across the Rhine in just 10 days to intimidate the Germanic tribes. It was not just a structure for crossing, it was a psychological blow. The Romans could walk on water wherever they wanted. The river, considered a natural border and protection, ceased to be an obstacle. The technology for building pile bridges on fast-flowing rivers was perfected to the point of automatism. Soldiers used special rafts and pile drivers, mechanisms for driving piles into the riverbed. Heavy loads were lifted on ropes and dropped onto logs, driving them into the ground to the beat of rhythmic songs. The piles were driven at an angle against the current to resist the force of the water, creating a reliable support. This sloping structure acted as a breakwater, cutting through the flow. Cross beams were laid on top of the piles and fastened without a single nail, using only grooves and ropes. The decking was made of tightly fitted planks, sprinkled with earth so that the horses would not be frightened by the noise of the water and the echo of the wood. In front of the bridge, bulls were installed, protective piles that broke up logs or ice floes floating downstream that threatened the supports. The entire structure was flexible, but incredibly stable. To build stone bridges, the Romans used caissons, watertight boxes lowered to the bottom. Water was pumped out of them using Archimedes' screws or water wheels, allowing workers to dig the foundation on the dry riverbed. It was dangerous and hard work, but it made it possible to place the supports on a rock foundation. The stone bulls of the bridges were pointed in shape to cut through the water and reduce turbulence. The arches of the bridges were erected using wooden centering, temporary frames that supported the stones until the keystone was installed. Once the central stone was in place, the arch began to support itself under the force of gravity. Roman arches were semicircular, which required massive supports but provided enormous load-bearing capacity. Many of these bridges are still standing today and are used for vehicular traffic. Bridges were often built as part of fortifications, with towers and gates on the banks. This allowed the crossing to be controlled and tolls to be collected from merchants. The bridge was a bottleneck where an enemy army could easily be stopped. In case of danger, the wooden spans could be quickly dismantled or burned, cutting off the enemy's path. The speed of bridge construction was achieved by working simultaneously on both banks and using many boats. Materials were prepared in advance and brought to the water at the right moment. Engineers calculated the design so that the force of the current could be used to install some elements. The river became not an enemy, but an assistant to the builders if they knew how to deal with it. Roman bridges symbolized the connection between the provinces and the center. They destroyed the isolation of the regions, making the empire a single whole. Where people used to cross in flimsy boats, now legions marched and heavy carts drove. It was a victory of geometry over the chaos of the water element. The most impressive example was Trajan's bridge across the Danube, over a kilometer long, with wooden arches on concrete supports. To the barbarians, this structure seemed like a wonder of the world, created by gods rather than humans. Demonstrating technological superiority often worked better than open combat. Enemies understood that it was useless to resist a nation capable of encasing a river in stone. Bridges were the most vulnerable and complex infrastructure objects, requiring constant maintenance. But even their ruins today inspire awe with their monumentality. How do you think the Romans coped with the task of providing accommodation for an entire army in the open field every night? The Roman army never slept under the open sky without protection. At the end of each day's march, no matter how exhausting it was, the legion built a fortified camp, a castrum. This was not a chaotic cluster of tents, but a full-fledged city with streets, a square, and defensive structures. The entire process took only a few hours, from arrival at the site to complete readiness for defense. As soon as the vanguard chose a location, surveyors marked the perimeter and main axes of the future camp with colored flags. The legion's standard was placed in the center, and from there the geometric layout of the territory began. Each centurion knew exactly where his unit's tent should be pitched. The soldiers threw down their packs and immediately grabbed shovels, while others stood guard. A deep V-shaped ditch was dug around the perimeter of the camp, and the earth was thrown inside, forming a high rampart. A palisade of stakes, which each legionnaire carried with him, was erected on the rampart. These stakes, pila muralia, had pointed ends and were fastened together to form a continuous wall. In a matter of hours, a fortress grew up in the open field that was impossible to take by surprise. Inside the camp, tents were set up in neat rows with wide aisles. This was done not for beauty, but so that in case of alarm, soldiers could quickly assemble and go to the walls without jostling. The space between the tents and the rampart was left free so that enemy arrows and spears could not reach the sleeping people. Pack animals and trophies were also kept here. The Castrum had 4 gates, one on each side, protected by special embankments and towers. The gates were a weak point, so they were designed to force attackers to expose their unprotected side to fire. The night guard on the walls changed every 3 hours at the sound of a trumpet. The password system changed every day to prevent spies from infiltrating. If the army stayed in one place for more than one night, the tents were replaced with wooden or stone barracks. The earthen rampart was reinforced with turf or stone, and the moat was deepened. The temporary camp was transformed into a permanent base with a hospital, workshops, and baths. Many modern European cities, such as Vienna and Manchester, grew up on the sites of such Roman camps. Sanitation in the camp was of the highest standard for the time. Latrines, toilets, were always located at the edge of the camp, downstream or on the leeward side. Garbage and waste were removed and buried outside the walls. This prevented epidemics, which often killed armies faster than enemy weapons. Hygiene discipline was as important as military discipline. The speed with which the camp was dismantled was as impressive as its construction. At the sound of a trumpet, the tents were folded, the stakes were pulled out of the rampart, and the columns set off, leaving only earthen ramparts behind. Enemies pursuing the Romans encountered an empty but formidable fortress every morning. This demoralized the enemy, demonstrating an unattainable level of organization. The Castrum was a soldier's home, an island of Roman order in the chaos of the barbarian world. Behind its walls, a legionnaire felt safe, could eat hot food and repair his equipment. This psychological sense of security allowed the army to maintain its morale during long campaigns far from home. Every evening, the same ritual of creating order out of nothing was repeated. Millions of cubic meters of earth were dug up by Roman shovels over centuries of expansion. The Roman Empire was built not only with the sword, but also with the legionnaire's shovel. Water is life, and the Romans understood this literally. To turn their conquered lands into prosperous provinces, they needed to provide their cities with clean water. Aqueducts were the pinnacle of hydraulic engineering, delivering water from mountain springs tens of kilometers to the centers of civilization. These were not just ditches, but complex artificial rivers flowing over bridges and through tunnels with a mathematically calculated slope. The secret of the aqueduct was a constant, barely noticeable slope that made the water flow under the action of gravity. Engineers used special instruments, called horobati, to maintain a slope of several centimeters per kilometer of the route. If the slope was too steep, the water would erode the channel. If it was too shallow, the water would stagnate. The precision of these calculations over such vast distances is astonishing even today. Most of the aqueduct ran underground in stone tunnels, protecting the water from evaporation and contamination. Only when crossing valleys and ravines did the water rise to the famous arch bridges. These majestic arcades, which we are used to seeing in pictures, were only a small part of the entire system. The underground channels required enormous earthworks and the digging of pits for ventilation and cleaning. Inside, the canal was covered with special waterproof cement so that not a single drop of precious moisture would seep into the ground. The corners were rounded so that water would not stagnate and dirt would not accumulate. At certain intervals, sedimentation tanks were installed, where sand and debris settled to the bottom, purifying the water. The quality of the water was a source of pride and concern for the authorities. As it approached the city, the water entered the Castellum Aquae, a huge distribution reservoir. From there, it flowed through lead and ceramic pipes to public fountains, baths, and the homes of wealthy citizens. The system was designed so that in case of water shortage, private homes were the first to be shut off, followed by baths and only lastly public fountains, which were accessible to everyone. The construction of the aqueduct required the digging of tunnels through the mountains. Workers cut the rock from both sides, meeting in the center with an error of a few centimeters. To destroy the hard rock, they used the fire drilling method. The rock was heated with fires and then rapidly cooled with water, causing it to crack. It was hellish work in the dark and stuffy conditions, but it produced results. Aqueducts allowed Roman cities to maintain unprecedented levels of hygiene. Baths, or thermal baths, consumed enormous amounts of water, becoming centers of public life. The sewer system, the Cloaca Maxima, carried sewage away from the city, preventing disease. The Romans washed more often and lived in cleaner conditions than Europeans for the next 1,500 years. A special service headed by the curator of waters was responsible for maintaining the aqueducts. Teams of slaves constantly cleaned the channels of calcium deposits, repaired cracks, and fought illegal taps. Water theft was a serious crime punishable by fines and confiscation of property. Water was a state resource of strategic importance. Behind all this grandiose construction was not only the muscle of the legionaries, but also the outstanding intellect of the managers. Roman engineering management was a system that was thousands of years ahead of its time. Large projects were headed not just by officials, but by professionals who had risen through the ranks from simple soldiers or architects. The camp prefect or construction supervisor had full authority and responsibility for the outcome. Planning began long before the first pickaxe strike. Scouts drew up detailed maps of the area, assessed resources and possible risks. Projects were approved taking into account logistics, deadlines, and budget. The Romans were the first to use network planning, dividing complex tasks into stages in parallel processes. While some were digging the foundation, others were already cutting down trees for the roof, and still others were firing bricks. The division of labor was taken to the extreme. There were no universal workers on the construction site who did everything. Bricklayers laid bricks, carpenters worked with wood, blacksmiths forged staples. Unskilled slaves and soldiers only did rough work, such as carrying heavy loads and digging the ground. Everyone did what they did best, increasing overall productivity. Quality control was strict and multi-stage. Each section of the wall was the responsibility of a specific centurion who put his mark on the work. If the wall collapsed, the guilty parties were found immediately, and the punishment was severe, even decimation, the execution of every 10th man, in special cases. But more often, a system of incentives was used. Distinguished troops received double rations, money, and exemption from duty. Documentation was kept with meticulous accuracy. The archives stored drawings, estimates, and reports on material expenses. This made it possible to analyze the experience of past construction projects and avoid repeating mistakes. Knowledge was not passed on orally, but through technical treatises, such as the books of Vitruvius. The engineering school was systematic, accumulating and multiplying the knowledge base. The Romans knew how to delegate authority to local authorities, demanding results but not interfering in minor details. Colonial cities were required to maintain roads and walls at their own expense. This created a decentralized infrastructure support system that worked on its own. The empire set the standards and the provinces implemented them. Contracts with private contractors, publicans, who undertook the supply of materials or the construction of individual facilities, played an important role. A system of tenders and auctions allowed the state to select the best offers. Corruption, of course, existed, but it was fought ruthlessly, understanding that the security of the state depended on the quality of the concrete. Engineers constantly experimented with new materials and technologies. If they saw a successful solution from their enemies or neighbors, they immediately copied and improved it. Roman pragmatism knew no pride. Anything that worked had to serve Rome. They absorbed knowledge from all over the world, remolding it into their own system. The Roman Empire fell, but its stone skeleton remained standing, defying time. The roads built for the legions became the arteries of medieval Europe and the basis for modern highways. Aqueducts continued to supply cities with water, even when the secret of concrete was forgotten. Fortresses were transformed into feudal castles and the centers of future metropolises. The Romans built so thoroughly that it was more difficult to destroy their creations than to build new ones. The phenomenon of Roman construction lies in the fact that it shaped the landscape of modern Europe. State borders, the location of cities, canal beds, all of this is largely the legacy of Roman engineers. We live on foundations laid by people in sandals and with bronze compasses. Their geometry became our geography. But Rome's most important legacy is not stones, but an idea. The idea that humans are capable of changing the world around them, bringing order to chaos, and creating an environment suitable for life. An engineering approach to solving state tasks, large-scale planning and standardization, all these principles form the basis of modern civilization. We still use Roman law, the Roman alphabet, and Roman principles of architecture. The speed of Roman construction remains an unattainable ideal for many modern projects. Bureaucracy, approvals, and material savings often make us slower and less efficient than ancient builders. The Romans were not afraid of grandiose tasks and did not look for excuses. They simply took action and relied on discipline and reason. By studying their methods, we understand that technology is only a tool. The main strength lies in the organization of people, in the ability to unite thousands of efforts into a single vector. The Roman legion showed that collective labor, multiplied by knowledge, can work wonders comparable to those of the gods. A question for you: what do you think of this episode? Were you surprised by the speed and organization of ancient builders? If you want to learn more about the technologies of the past, be sure to subscribe to our channel and click on the bell. Suggest topics for future videos that you would like to see in the comments. Maybe your comment will be the basis for the next script.